So for the algebraic type problems here where we're solving inequalities algebraically, the first thing we want to do is we want to factor. Okay, so we want to factor the left side, x plus 3x minus 3, still greater than 0. And then we want to set our factors equal to 0 and find the zeros. Okay, so the zeros are x equals negative 3 and x equals positive 3. Okay, and once we find the zeros, we want to set up a sign chart that determines that we will be able to determine the sign of the function on the separate intervals. Now, one thing to keep in mind, when we separate our number line into different intervals, what we're really doing here is breaking up our inputs, okay, and or breaking down the inputs, whatever you want to think about it. But the interval to the left of negative 3 is basically where the function's values are either going to be positive or negative, okay, and that interval to the left of negative 3 is the interval from negative infinity to negative 3, and then the interval in between the two would be the interval from negative 3 to 3. And then to the right of 3, we know that that's the interval from 3 to infinity. So our sign chart, once again, remember that the only zeros of the function f of x equaling x squared minus 9 are the zeros negative 3 and positive 3. So what we know about polynomial functions is that if we don't have any more zeros, then the function, if it's positive for any number on the interval from negative infinity to negative 3, then it's going to be positive for all values of x on that same interval. So all we have to do is test one value on the interval, because all the other values are going to provide us with either the same, are going to provide us with the same sign. So let's go ahead and start this. Negative 10 is going to be my test value. If I replace x with negative 10 in either one of these, either the factored form or the non-factored form, I can see that 10 squared here is 100 minus 9. That's going to be a positive number. Or I could think of it as 10 plus 3 is positive, times 10 minus 3 is also positive. So either one, we should see that the function's values will be positive on that entire interval, okay, from all real numbers less than negative 3. Then on the interval from negative 3 to 3, we have to pick another test value. The test value of 0 is a nice one because it's easy to plug 0 in for x. And we can see in either one we'd get negative 9, and therefore that function will be negative over that entire interval, over the interval from negative 3 to 3. Likewise, if we choose any real numbers to the right of 3, that's any real numbers greater than 3, when we square that number, let's say we choose 10, or we even choose 4, but 10, again, 10 squared is 100 minus 9. That's again going to give us positive values for f of x. Okay? So without graphing it, we already know that the values functions, function's values are going to be positive on this interval here and this interval here, which we already have written those intervals out. So we would say that x squared minus 9 is greater than 0 on the interval from negative infinity to negative 3, combined with the interval from 3 to infinity. Okay? Whatever you do, please do not say x is greater than 3 and negative 3. Because that's the common mistake students make. They don't think that they have to create a sign chart here. And the problem is that they just kind of try to memorize a process. They look at this inequality without understanding that as x changes throughout the domain of the function, as the inputs change, the outputs are going to change from positive to negative to positive. That's why it's kind of nice if you understand the concept of graphing the function. If you think about the graph of the function, we know that x squared minus 9 looks like this. Okay, here we have negative 9 down here, and here, guess what? We have negative 3 and we have positive 3. So this sign chart tells us what the graph tells us quickly, but it takes a little longer to do the sign chart. So that's why I encourage you to not only know the sign chart, which you do have to know how to do, because you're going to be applying that in different areas of calculus as well. Nevertheless, you need to know both methods, because the graphing method helps you go fast. The sign chart method is going to help you do things later on that you're going to need that skill for. Okay, so that's solving algebraically. You try, should you try this one? Yeah, go ahead and pause the video if you'd like to give it a shot on your own. I have another practice problem for you, but nevertheless I'm going to walk you through this one. X minus 6 times x plus 3 is greater than or equal to 0. Okay, and then we have zeros of 6 and negative 3. Those are the values we place on our number line, breaking up our domain into 1, 2, 3 intervals. We can see they're separated by the negative 3 and the 6. So the first interval from negative infinity to negative 3, we're going to pick a test value of negative 10 again. Negative 10, I like to put it, once the numbers start getting really big, I like to plug it into this here. So we can see negative 10 minus 6, that's a negative factor, and negative 10 plus 3, that's also another negative number. So any real number to the left of negative 3 is going to cause both factors to have a negative value. Therefore, negative times a negative gives us a positive. Okay, and then in between negative 3 and 6, again, 0 is a nice choice. 0 minus 6, that's a negative factor. 0 plus 3 is a positive factor. So we see, once again, we have basically the same thing going on. Positive interval, then negative, then positive again. Greater than 6, we can see positive times a positive. Okay, and therefore this function x squared minus 3x minus 18 is greater than or equal to 0 on the interval on intervals from negative infinity to negative 3, including though negative 3, combined with the interval from 6 including 6 all the way to infinity. Okay, so that's how to solve polynomial inequalities algebraically. Now let's do rational inequalities algebraically, and I'll do the first one, you do the second one. How's that? No, I'll do the second one. It's harder, so I'll do the second one. And yeah, let's start with an easy one, and then we'll go to the harder one, and then I'll give you another practice problem. Sorry for the confusion. I changed my mind obviously a few times here. So the first thing we're going to do is, not only for rational functions we have different things going on. In other words, we have sometimes domain restrictions. So the first thing we're going to do is figure out the zeros, and that's when the numerator is equal to 0, and that's when x is equal to 1. And then we find when the function does not exist. Okay, the rational expression is undefined. So d and e, that's when the denominator is equal to 0. Okay, so that's when x is equal to 3. So these are the two values that become what we call critical values for our function, and we have to make a sign chart, and we're going to put both of those critical values right there. We know that at x equals 3 we have a vertical asymptote on the graph of the function, but nevertheless, breaking up our intervals just like we did the last time with the polynomial functions. And to the left of 1 we can choose 0. Now here we're just going to replace x with 0 in this for the fraction, x minus 1 over x minus 3. 0 minus 1 over 0 minus 3, we can see that that's a negative divided by a negative. Well, that's positive. Okay. Then in between 1 and 3, let's pick 2. 2 minus 1 is a positive number, but 2 minus 3 is a negative number. So we end up having a positive divided by a negative, which we know that's negative. Okay. And then to the right of 3, let's pick 5. 5 minus 1 gives us a positive number. 5 minus 3 gives us a positive number. In fact, any number bigger than 3 is going to be positive divided by a positive, so therefore positive values for the function to the right of 3. So now we have everything we need. Okay. One thing though, I did forget to mention that when you put these numbers down here, the 1 and the 3, the 0, I want you to put equals 0 down below the x equals 1, which is a 0. I want you to put that when x is 1, the function's values are 0, or the function's value is 0. And then when x is equal to 3, we know that the function does not exist. Because if you have a d and e underneath a number, whether it's greater than or equal to or less than or equal to, you'll never include this value in the solution because you can't. The function's values never exist when you have a D and E there. That's why you put the D and E there. So now again, we've got everything we need. Let's highlight the area that's going to be, we have greater than. You always have to look back. Greater than, so we're looking for when the function's values are greater than. Okay, so on these two intervals. And so we have on the interval from negative infinity to 1, not including 1, because greater than right there. If we're greater than or equal to, then be a bracket. Combined with the interval from 3 to infinity, and that's our answer. Okay? That's it. I'm at the 11-minute mark. I'm going to try to do this in the next 4 minutes. So let's go ahead and get started with number 4. Factoring the numerator, x minus 7 times x plus 1. And then we have x plus 1 times x minus 1. Nevertheless, I don't think we need to worry about that these two factors will cancel. Just don't cancel them yet. Yeah, there is a reason why we need to acknowledge here. We don't have an x-intercept when x is equal to 1. Or, sorry, when x is equal to negative 1, we don't have an x-intercept. So the zeros of the function, zeros, are x equals 7. Okay, and then the D and E of the function are when x equals negative 1 and when x is equal to 1. Okay, therefore, when we construct our sign chart, we have negative 1, 1, and 7, and underneath, what color did I do that in? Orange. Okay, underneath the negative 1, we have to put D and E, because our function does not exist when x is negative 1. Okay, it's going to be a hole there in the graph, as you may have recognized. We're going to have a vertical asymptote at x equals 1 if we were to graph the function, and then equals 0, the function's values are equal to 0 right there where x is equal to 7. So then, to the left of negative 1, we have, let's say, negative 5, and we can replace x with negative 5 in our simpler version, our simplified or our reduced function here. So this is our reduced function, simplest terms, or simplest form. Okay, so we can just replace x with the negative 5 or these other test values into this form, because even if we replaced x with those values in the one up here, the original function, those numbers would cancel out anyway, so we don't need to worry about using just this simpler form here. Alright, so when we replace x with negative 5, we get negative in the numerator, negative in the denominator, negative divided by negative is a positive. Okay, in between negative 1 and positive 1 we have 0, and 0 minus 7 over 0 minus 1, that's a negative divided by a negative again, so we have positive, positive again. Between 1 and 7, let's pick 3. 3 minus 7 is negative, 3 minus 1 is positive, so therefore on that interval the y values are negative. And then to the right of 7, let's pick 10, positive divided by a positive, and we get a positive. Okay, but we want the interval on which this function's values are less than or equal to 0, and the only place that we have that is right here. So I picked a good problem because look, we've got a D and E and we have an equals 0, and so we would say that x squared, can you see that still? X squared minus 6x minus 7 all over, I'm barely squeezing in here, x squared minus 1, okay, you can still see it, is less than or equal to 0 on the interval from, be careful here, the D and E means we can't include 1, but we go all the way to 7, which is equal to 0. Function's values are equal to 0 there, and so we have this interval right here. So the answer to the question is, on the interval from 1 to 7, this, let me say it a different way. This rational function is less than or equal to 0 for all real numbers between 1 and 7, including 7 but not including 1. Okay? So that's it. Let me show you the problems that I'd like you to do. And in the next video I will show you the solutions to these. But I'm almost at my 15-minute mark. So pause the video, write those down, and I'll see you in the next video.